right, let's look at our next Raoult's law example. So this is exercise 4. So this is problem 4 from the course textbook. So assuming normal heptane and normal octane, so that's C7 and C8, form an ideal solution, do the following. All right, so it's definitely reasonable to assume that C7 and C8, these two linear alkanes mixed, to form an ideal solution. All right, in an ideal solution, we assume all of our intermolecular interactions are exactly the same. So A, calculate the chemical potential of heptane and octane at 40 degrees C, 1 bar, and x1's 0.45. B, calculate the fugacity at the conditions of part A. And then C through F, we're calculating bubble points and dew points. And then G, we have a flash calculation. Okay, so let's just start with A. Okay. So A, looking at it initially, it seems like a piece of information must be missing in that you can't just calculate an absolute chemical potential. It has to be relative to something. All right. So let me write out what I would assume they are. Right. So just if I was just blindly going at it, and so if I had to calculate the chemical potential of a component in a mixture, how am I going to go about that? Well, okay, since I don't memorize everything, okay, I remember that delta G of mixing, okay, for my ideal solution, so I'll skip the ID, okay. Remember, the term to remember is sum over I, xi log xi, okay. When it comes to G, okay, well, we know delta G of mixing is going to be less than or equal to 0. All right, so except to the pure component limits, right, we expect delta G of mixing to be less than 0. So log xi will be less than 1, except in the pure component limits. So this will be negative. So this must be positive RT, right? RT has the units of G, energy, positive, so the delta G of mixing is negative, okay? So now delta G of mixing is RT sum over I xi log xi, okay? And delta G of mixing is, by definition, G minus sum over I xi gi, where G is sum over I xi g bar I minus sum over I xi gi. So collecting terms, okay, what I'm going to do here, I'm going to bring RT in since I'm mixing at constant temperature and pressure. So I'm going to write this as sum over I xi RT log xi is equal to, collecting terms over here, sum over I xi g bar I minus gi. Okay, these two expressions are equivalent, so the terms in parentheses must be equivalent for them to be consistent with each other. So it must be that g bar I minus gi is equal to RT log xi, where g bar I, right, this would correspond to my chemical potential of component I at Tp and composition xi. Remember, g bar I and mu I are equivalent, minus gi, that's my pure component value at T and P, and that's going to be equal to RT log xi. Okay, so where I say I think they're missing, reference state here, is we're asked to calculate the chemical potential of heptane. Okay, and we're given the temperature, pressure, in liquid phase, mole fraction. Okay, so I know the liquid phase mole fraction, so I know RT log xi. Okay, mu I is what I'm trying to calculate. So the question is, do I know GI? Do I know the pure component molar Gibbs free energy? Right, the answer is no, because it comes back to needing to define a reference state in some way. All right, so if we're given an idealized state as a system at, say, the same temperature but a different pressure, or pure component state at the same temperature but a different pressure, I could use that to define my zero, calculate G by integrating the appropriate expression with respect to pressure, And then I would know that and RT log xi, so I could get mu I. So for A, I think that the best you could do is you could calculate mu I relative to GI. So you calculate the chemical potential of C7 in solution relative to the molar Gibbs free energy of pure component I at the same temperature and pressure, right? And that's just going to be equal to RT log xi, where you're given x1, so you have that term. Okay, cool. Okay, B, calculate the fugacity of normal heptane at the conditions of part A. Okay, so calculate the fugacity of normal heptane at the conditions of part A. Okay, so we're told to assume they form an ideal solution. Okay, so without doing any calculations, because in C, D, E, and F, we're going to do bubble P and dew P calculations. Okay, so without knowing what the dew point and bubble point are for that mixture of this composition, I'm just going to assume that I have a liquid phase, right? I'm going to assume I have a liquid phase. I'm trying to peek ahead, and it doesn't look like I. So ideally, what I should do for B is I should do a bubble P and dew P calculation, which we'll do next, and then use that to confirm that I have a liquid, right? But I'm going to assume I'm in that liquid region, okay? And then we're told that we have an ideal solution, okay? And so if I need to calculate the fugacity of an ideal solution, okay, remember that the fugacity of component I in an ideal solution, okay, so ideal solution, we're thinking liquid phase, okay? So that's why I said we do the dew P and bubble P calculation to confirm that we have a liquid. So I confirm I have a liquid, that we're told to assume that it forms an ideal solution, okay? And so if I have an ideal solution, okay, then the fugacity component I in my ideal solution will just be xi, mole fraction, times Fi pure, okay? Where Fi pure, okay, well, that's going to be equal to, okay, and this is going to be Fi pure at given temperature and pressure, would be equal to Phi sat at T, Pi sat at T, okay, remember this is nothing more than Fi sat at T, so fugacity of pure component I, okay, times my Poynting correction, integral V over RT dP from P sat to P, okay. This is my Poynting correction, and this is just Fi at T and P relative to Fi sat at the same T, okay. So I need to calculate Fi pure, okay. Well, are we given information to even calculate the Poynting correction? The answer is no, okay. But again, if I assume that I'm in that compressed liquid region, okay, and compressed liquid region, so well removed from the critical point, and then if I look at that Poynting correction, if I assume that the molar volume is incompressible, right, it becomes a V over RT times P minus P sat. So if I assume that term P minus P sat is relatively small, so what do I mean by small? Is it on the order of a bar, or is it on the order of 1,000 bars? So if it's on the order of a bar, then typically you can assume that Poynting correction is negligible. Okay, and here our system is at 1 bar. Okay, so I'd have to imagine that our Poynting correction, that P minus P sat term, right? And you could go and calculate your corresponding P sats. But I'd assume that this term is approximately equal to 1, is negligible. Okay, again, you could go and calculate. Are we looking at component 1 or component 2? We're looking at heptane. So you could go to your Antoine equation for C7. You could calculate P1 sat. Okay, now you don't know the molar volume, but you could calculate P1 sat, compare that to 1 bar, and see that that's going to be pretty small, right? In fact, it's going to be less than 1, and so that term should be pretty negligible. Okay, so Poynting correction we would assume is negligible. Then if we assume that our vapor phase is an ideal gas, right? Of pure component 1, again, we're at low pressures, so assuming vapor phase is an ideal gas, should be a reasonable approximation, okay? And then we're just left with the fugacity of component I, and our ideal solution is going to be xi times pi sat, okay? So you calculate vapor pressure of component I at saturation at the temperature of interest. We know the composition, so I can calculate the fugacity then of component I in that ideal solution. Okay, cool. So I can't calculate absolute chemical potential because we're not given a reference state, but I can calculate an absolute fugacity. C, calculate the bubble pressure of the solution at x1's 0.45 and 40 degrees C. Calculate the dew pressure of the solution, assuming that the solution x1 is 0.45 and 40 degrees C. So C and D calculate the bubble point pressure and dew point pressure. Then E and F are repeating with temperature. Okay, so let's look at C and D together. So if I'm looking at C and D, so if I have a mixture of x1 0.45 at temperature of 40 degrees C, and I want to calculate P bubs and P dew, I immediately think of a PXY phase diagram. Okay. So problem C and D, right, are going to be one and the same. Okay, where I'm going to sketch a PXY. Okay, so PXY, so P1 sat is going to be larger than P2 sat. Okay, bubble line is going to look like a straight line. Okay, we are told that our temperature is 40 degrees C, or 40 degrees C, and our composition is 0.45. So our temperature is 40 degrees C. Okay, we're looking at a mixture, okay, with the composition Z1 is equal to 0.45. Okay, high pressures favor liquid. Low pressures favor vapor. Okay, so this is my bubble line. This is my dew line, where my, where if I'm moving along my line at constant composition, so I'm keeping temperature and composition constant and changing pressure. Okay, this would correspond to my bubble point. This would correspond to my dew point for that mixture, right? Bubble point pressure and dew point pressure. Okay. What's unique about my bubble point, okay, that's where I transition from liquid phase to two phase. Okay, so at my bubble point, x1 is equal to z1. At my dew point, okay, then I have y1 is equal to z1. Okay, so I think that's all we're given, right? And you're given P1 sat and P2, or you're given T, and since you know T and you have the Antoine expressions, you can go ahead and calculate P1 sat and P2 sat. Okay, but if I want to calculate my bubble point and dew point pressure, okay, we're going to do what's called a bubble P and a dew P calculation. Okay, so what's a bubble P calculation? So if I'm looking at my system at my bubble point, I have a system at two-phase coexistence. So I can go ahead and write down my isofugacity expression. Okay, so we've already been told we can assume our liquid phase is an ideal solution. We'll go ahead and assume that the vapor phase forms an ideal gas. Again, we're at relatively low pressures. Okay, so if I think about my bubble P, okay, so calculate the bubble point pressure, I write down my two isofugacity expressions. Y1P is equal to x1 P1 sat. Okay, so here we're using Raoult's law. Okay, the idea is we know the temperature, so then via my Antoine expression, I know P1 sat and P2 sat. Okay, I know x1 and x2, because at my bubble point, x is just equal to z1, the composition of my mixture, so I know my liquid phase compositions. I don't know y and I don't know p. Okay, p is what I'm interested in. I'm interested in my bubble point pressure. So the trick then is to add the two equations together to kill y. Okay, y, so if I add these together, all right, looking at the left-hand side, I'll have y1p plus y2p. That's the same p, so I can factor it out. write it as P times y1 plus y2. Okay, well, y1 plus y2 is just equal to 1. So when I add these two equations together, I get P, okay, and this is going to be P bubs. P bubs will just be x1 P1 sat plus x2 P2 sat. Okay, and just for completeness, because we're going to do a do P calculation next, all right, at my bubble point, x is equal to z. So you can think of this as z1 P1 sat plus 1 minus z1 P2 sat. Okay, where z is just the composition of our mixture, which is 0.45. All right, you know the temperature, 40 degrees C, so you have P1 sat and P2 sat. Okay, if I want to know the dew point pressure, okay, here, okay, I do a dew P calculation, okay, which is going to essentially be, you know, the same thing in spirit. Okay, at my dew point, I have a two-phase system at vapor-liquid coexistence. So I write down my two isofugacity expressions. Okay, so I know the temperature. Okay, so I know P1 sat and P2 sat. Now I know Y1 and Y2 because at my dew point, my vapor composition is equal to the composition of my mixture. What I'm interested in solving for is P. So P is what I want. Okay, I don't know X1 and X2. Okay, so in the same spirit of a bubble P calculation, is I want to add the two equations together so that I kill X. Okay, but in order to do that, what I first need to do is rewrite the equations. Okay, and before I do this, I should even take a pause though. That, you know, I know that X2 is equal to 1 minus X1. So here then I have a system of three equations with three unknowns, X1, X2, and T, right? P1 sat and P2 sat are only functions of T if I were to plug in my Antoine equation. And I could just take those three equations and directly solve them for X1, X2, and T, right? I could do that, okay? And do P calculation though, right, it's going to try and isolate P, okay? And so the trick to do that is I'm going to rewrite this as divide the left-hand side by P1 sat, divide the left-hand side by P2 sat, right? This is P times Y1 over P1 sat is equal to X1, P times Y2 over P2 sat is equal to X2. Okay, so if I add them together, the right-hand side is just going to be equal to 1. Okay, actually I'm going to write a big, right, equal sign. So, okay, P is the same. Okay, so this becomes P times Y1 over P1 sat plus Y2 over P2 sat is equal to 1. So solving for P dew then, right, I get the P dew, the dew point pressure is equal to Y1 over P1 sat plus Y2 over P2 sat inverse, right, the inverse of that, okay? So again, I know the temperature, so I can solve for P1 sat and P2 sat. I know Y1 and Y2, right? It's just the composition of my mixture. So I can use that to readily solve for P dew. Cool. Okay. All right. So then, you know, if I were to look at E and F, it's essentially the same thing, only now we're asked to calculate the, let's see, C and D, we calculate the pressure. E and F, we're calculating the temperature. Okay, so let me add another page. Okay, and you know, actually, in theory, I don't even need to rewrite it. Okay, oh, I need to insert the page after here. Okay, so what do I mean by that? Okay, so you know, you could draw a TXY phase diagram, and that would certainly help you out. Okay, but you know, in the interest of time. Well, okay, let's write it out for completeness. So this is C and D. So E and F. Okay. So that was my PXY, solving for my bubble point pressure and temperature, or bubble point and dew point pressure. Now I want to solve for the bubble point and dew point temperature. So I'm going to draw TXY. Okay. So for component 1, I'll have the larger, I'll have the lower pure component T1 sat. Okay. Here's 2 sat. Connect those two via curve. Okay. So the labeling that we have in E and F is I'm going to have that same mixture of 0.45 mole fracs, and we're going to have a pressure of 1 bar. Okay, so my pressure, constant equal to 1 bar. I'm going to draw my line of constant composition for Z1 is equal to 0.45. Okay, so now low temperatures, all right, this would favor my liquid. High temperatures up here are my vapor, in between 2 phase. Okay, so that would make this my dew line. This is my bubble line. Okay, this would correspond then to the dew point and bubble point of my mixture. Okay, so at my dew point, okay, same thing, all right, here's Y1, here's X1. So at my dew point, what's special is Y1 is equal to Z1, all right, my vapor composition is equal to the composition of my mixture. At my bubble point, okay, X1 is equal to Z1, the composition of my mixture. Okay, cool. So the pressure is 1 bar. So I could solve for T2 sat and T1 sat if I wanted to. I just go to my Antoine equation, plug in a pressure of 1 bar, and solve for T from the 2 corresponding Antoine expressions. Okay. So if I want to calculate the temperature of my dew point and bubble point, it's exactly the same procedure. Okay, and actually let me take one pause too, right, and mention, I had mentioned in A and B it'd be good to do my dew P and bubble P calculation first to check my phase, right? And again, why that's good is that if I have a pressure that's greater than my bubble point pressure, then I have a liquid. If I have a pressure that is less than my dew point pressure, then I have a vapor. In between, I have 2 phase. So if that pressure in part A and B were greater than my bubble point pressure, then I knew I would have a liquid, right? And so for a given mixture, it's useful to know my bubble point pressure and dew point pressure, or the location of that dew point and bubble point, so I can determine the phase. Okay, but anyways, coming back here, okay, if I want to calculate now the temperature of my dew point and bubble point, it's the same thing as doing a dew P and bubble P calculation. It's exactly the same. Okay, so if I first focus on my bubble point, okay, well, so it's the same thing, it's just a little more challenging to solve numerically. Okay, so if I look at my bubble point, it's the same thing. At my bubble point, I have 2 phases at vapor-liquid coexistence. So I write down my isofugacity expression. Okay. Okay, what do I have? Well, now I have P, okay. It's a bubble point, so I know X, because the X is just equal to my mixture composition. I don't know Y, okay. And I don't know P1 sat and P2 sat. But remember, these aren't 2 independent variables, right? When I look at P1 sat and P2 sat, what's important to remember is they're only functions of T, right? Remember, this is a pure component system at vapor-liquid coexistence. So I have just a single degree of freedom, all right? And so I'm using my Antoine expression. So, if I specify T, all right, if I know T, then I can calculate corresponding pure component vapor pressure. Okay, so when I see P1 sat or P2 sat, I just think of T. All right, same variable. Okay, and that's what I want to solve for. Okay, so I want this. Okay, look at the left-hand side. I don't know Y1. Okay, so just like when we did our bubble P calculation before, I'm going to add the 2 equations together to kill Y. Okay, so adding them together, I'll get P, right? Because Y1 plus Y2 is just equal to 1. Is X1 P1 sat plus x2 p2 sat. Okay, where again here now I know p, I know x1, I know x2, but I don't know temperature. Okay, so I'll need to solve for the temperature so that this equation is satisfied. Right, I've reduced this to one equation with one unknown. So this is where I say in theory it's the same as when we did our bubble p calculation, but now it's a little more of a pain in the neck to solve, right? And so you might want to think about solving it, say numerically. You could use Excel, or you could readily use MATLAB to calculate the bubble point temperature. Okay, but it's the same thing. It's just a little harder to solve. Okay, for the dew point temperature, well, it's one and the same as when we did it before. Okay, at my dew point, two phases at vapor liquid coexistence. Oh, let me write them over here. Okay, so at my dew point, I have two phases at vapor liquid coexistence. So I write my isofugacity expressions. Okay, dew point, I know y because y is just equal to my mixture compositions. Here we're told what our pressure is, right? We think about it Txy, pressure is known and fixed. I don't know x, okay, and I don't know t, right? So I don't know P1 sat and P2 sat, okay? But P1 sat and P2 sat, remember I think of those, I just think of t, right? Because they're only functions of t. So my goal is to solve for t. I don't care about x1 and x2 in this case, okay? And so the trick is, rewriting this so I can add them together and kill x1. Okay, again, you don't need to do this. I could just solve it as is and get x1 at the same time, right? Think of this as two equations with two unknowns, but it's not necessary, right? But then again, if you use MATLAB, you can just solve it just as easily as solving just for p, okay? But anyways, so tackling this animal, what I'm going to do is I'm going to divide by P1 sat and P2 sat. So I'm going to write this as P times Y1 over P1 sat is equal to X1, P times Y2 over P2 sat is equal to X2. And I'm going to add them together, right? Because X1 plus X2 is just equal to 1. Okay, pressure is the same. So this becomes P times Y1 over P1 sat plus Y2 over P2 sat is equal to 1. Okay, so again, I know Y1 and Y2 is just my mixture composition. I know P1 sat and P2 sat, right? Essentially, if I knew T, then I would know them, right? So if I look at this left-hand side, the only unknown variable is T, all right? And so, I would solve it again numerically. Personally, I would use F0 in MATLAB to solve for the temperature for which this equation is satisfied. Cool. Okay. And then the very last question, G. Let's look and see what G is asking us. So G, calculate the amount and composition vapor and liquid when a solution with Z1 is 0.45 is flashed to 40 degrees C and pressure of 0.065 bars. Okay, cool. Okay, so now in theory, let's see, you could look at this in a couple different ways. C and D, right? At 40 degrees C, you would have calculated your bubble P and dew P. Okay, so again, the first check is this pressure in between my bubble P and dew P? Okay, and hopefully it is, right? I haven't done any calculations, so I can't check this. But the check that I want to do to make sure this problem is reasonable is that at 40 degrees C, you calculate dew P and bubble P. So if this pressure is between my dew P and bubble P, then I'm in the two-phase region of my phase diagram. Okay, so that's good. Okay, so I'm just going to go out on a limb. I'm going to assume that pressure is between dew P and bubble P, then I'm in my two-phase region and proceed. Okay, I'm just trying to take in everything. Okay, wish it wasn't so big. So I'm going to draw my schematic of a flash drum. Okay, and then we can go and label parts if needed. Okay, So I'm of an inlet stream of Z1, which is 0.45. Okay, we're going to send to our flash drum where we're told the temperature and pressure. Then out the top, we're going to have a vapor with flow rate V. At the bottom of a liquid with flow rate L. And let me label our inlet flow rate F. Okay, so let's go back up. Z1 was 0.45. Temperature is 40 degrees C and 0.065 bars. 0.065 bars. Again, I'm assuming that's in between P do and P bubs. I'm having not solved for P do and P dubs. I can't check, but I'm going to assume they're right. Yeah, 0.0645 bars. All right. So, here it's a matter of we can take it piece by piece. Okay. So first would be if we had just calculated P do and P dubs. Okay. So again, my first check is going to be check to make sure this pressure is between P do and P bubs. If it is, I have two phase, and we'll proceed as we will in a second. If my pressure is, say, less than P do, then I just have a vapor, right? So I just have a vapor coming off that's not in equilibrium contact. If my pressure is greater than P bubs, then I just have a liquid coming out, so everything's coming out liquid, right? That's not very interesting. So I'm going to assume I'm in between the two of them, that I have a two-phase mixture. Okay, and so if I do that, then this vapor stream will be in equilibrium with this liquid stream. Okay, so if we keep consistent with the last problems, we assume we have a system that's adequately described by Raoult's law. Well, then I can write down my isofugacity expression for my two components. Okay, so I have y1 p is equal to x1 p1 sat. Right, so I start by solving my equilibrium expression. Okay, so we're told that the temperature is 40 degrees C. What that tells me is I know P1 sat and P2 sat. I could plug into my Antoine expression and get P1 sat and P2 sat. Our pressure is 0.065 bars, so I have those. All right, so I have two equations with two unknowns that I could solve for y and x. Okay, because again, in theory, right, y1 plus y2 is equal to 1, so I could plug in y2 is 1 minus y1, x1 plus x2 is equal to 1, so x2 is 1 minus x1. Okay, you can solve it any way you want. One strategy might be to do a bubble P calculation, which you in turn solve for x, but it's entirely up to you. Okay, what's important though is you should see you have a system of two equations with two unknowns that you can solve and get y1 and x1. Okay, then remember the one subtlety in this book, right, is I have FV and L. Okay, so I can't solve for FV and L, right? I can't because, I have a single unit here. I have two components, so I have two mass balances I can write. Okay, two mass balances, three unknowns. Okay, and so what the book typically does, and they don't mention it, which is kind of frustrating, is you have to assume a basis, right? So basically, just assume that f is equal to 1. And actually, if I look at it, then if we assume f is 1, we can calculate v and l relative to 1. So it'll be essentially, relative amounts of v and l, right? So we'll assume that f is 1, and we'll calculate v and l, right? And so it would be, the fraction vaporized and fraction remaining liquid relative to what went in. Okay, so we just assume f is 1. The v and l we just get from mass balance. So I have two components, so I can write two mass balances. So I can write my, total mass balance is F is equal to V plus L. And I write my component mass balance is Z1F plus, Z1F is equal to Y1V plus X1L. where you just solve for y1 and x1, and you're given z1. Okay. Oh, and we assume a basis of f. So you have two equations with two unknowns, v and l. Again, I'll just leave it at that. I'll assume that you can solve those two equations simultaneously for v and l. Right? In theory, this is how we derived the lever rule previously. Okay. So this problem was a longer one, but that wraps it up.